Assalamualaikum.
Waalaikumsalam warahmatullahi.
Apa khabar?
Alhamdulillah, apa khabar semua? Alright, Assalamualaikum warahmatullahi wabarakatuh. Very good morning. Ladies and gentlemen, we are about to begin our session. Nanofabrication and Characterization. Please stand by. Okay, boleh dengar lah ya suara, boleh nampak kamera kan?
Boleh.
Alright, okay. I would like to seek for your kind cooperation to avoid any virtual disturbance during the live broadcast session. If you have any questions, the conference resource personnel are ready to attend you at the reception desk. Thank you for your kind cooperation and attention. We will start very soon.
Macam stewardess dah.
Kan? So nice to see everybody. Macam Syria pulang ke gagang tak?
Ya.
Alright, Bismillahirrahmanirrahim. I think we can start now, ya. Assalamualaikum warahmatullahi wabarakatuh. Very good morning. Ladies and gentlemen, welcome to the first Malaysia International Conference on Nanotechnology and Catalysis MICNC 2021. We are now in the session Nanofabrication and Characterization. My name is Mina Nakiah binti Ahmad Nizar, and I am a postdoctoral researcher at Malaysia Institute of Transport, MITRANS, UiTM. I will be the session chair today, together with the session moderator, Ms. Nurul Hazira Kamaluddin and Madam Nur Azimah Abdul Samad. Now, I would like to invite all the presenters to request to share audio and video. Okay. Okay, can we take the photo? Can we have the photo session now? Is that okay? All right. Okay.
Okay, I will take 2 photos. Hold on. Smile, 1, 2, 3. Okay, done.
All right. Thank you. Okay. Before we start, I think there are some announcements that I have to make. The oral presentations will be evaluated for the awards under 2 categories. The first category is Best Session Presenter, that will receive the certificate for Best Presenter, and I will announce at the end of the session. The Best Presenter Award that offered prize money from 500 to 1,000, trophy and award certificate. This will be announced during the closing ceremony. I would like to seek for your kind cooperation to mute your mic if you are not presenting and to avoid any kind of visual disturbance as possible. For those who intend to ask questions to presenter, you can channel your questions in the Q&A box. I will read it after every presentation. You can also request to share your audio and video to ask your question in live mode. Presenters are given 15 minutes for presentation and 5 minutes for Q&A session, whereas invited speakers are given 25 minutes for presentation and 5 minutes Q&A. I will remind the presenter to end the presentation 2 minutes before the presentation session ends. I will stop the presentation sessions when the session has exceeded the 5 minutes allowed. Before we start this parallel session, ni dah tadi kan? Okay. Without further delay, we will be hearing our first presentation from our first presenter, Mr. Muhammad Ishraf bin Aznam, with his presentation entitled Effect of Mixing Time of Precursor Powders on the Structural Properties of Nickel, Copper and Manganese Spinel produced by a glycine nitrate process. Okay, the stage is yours, Mr. Muhammad Ishraf.
Thank you, Ms. Director. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. I hope my voice is clear.
Yes, we can hear you very clearly.
Thank you. It is my pleasure to meet you all today. So my name is Ishraf Aznam. I am a PhD candidate from University Kebangsaan Malaysia. Today, I am happy to share a part of my research entitled Effect of Mixing Time of Precursor Powders on the structural properties of nickel copper manganese spinel produced via glycine nitrate process. So before I am going to discuss on the main content of this presentation, allow me to briefly introduce the background of this research. If we look over for the past 10 years, we can see the increasing trend for research in renewable resources. So one of the resources that is gaining interest is the biogas. As we all may know that biogas resources is abundant in most of the countries in the world. So as you can see in the picture, the resources can be in the form of livestock waste, crops, wastewater or food waste. In Malaysia, as the second world largest palm oil mill exporter, we have one of the most abundant biogas resources from the palm oil mill effluents. We also have wastewater treatment, which also can be directed to the anaerobic digester, which can produce biogas. So current situation is the technology used to produce biogas into heat and electricity is the combined heat power system. Produce a lot of harmful gases because the system involves combustion process. So there is an effort to replace the current technology with a more clean and affordable system which produce a lot more lower harmful gases and, if possible, without any combustion. Now, this is an example for an ideal system where a closed system is produced. So we want the byproduct of the system to have low carbon dioxide, which can be used again by the environment, or it can be used again by the system. So one of the technology that is gained interest is the solid oxide fuel cells. So the main benefit of the solid oxide fuel cells is that it can directly use biogas inside the system and reform the gas to be used as an electricity and heat. And also, the byproduct of the system is water and heat and also carbon dioxide, which is in a small amount compared to the current technology. Allow me to briefly introduce about the solid oxide fuel cells. So solid oxide fuel cells, like any other fuel cells, it produce electricity through electrochemical reaction without any combustion. As you can see here, it have three main components: cathode, electrolyte, and anode, where the fuel such as hydrogen is supplied to the anode and the oxidant is applied to the cathode. So the reaction will occur and the electrical energy will be produced at the anode. The main benefit of this fuel cell compared to the fuel cell is that the material used at the anode contain nickel, where the nickel is the frequent material used for methane reforming in produced syngas, which is hydrogen. So this allows the device to use biogas as a fuel to generate electricity. Furthermore, the temperature of the device is around 600 to 1000 degrees Celsius. So this temperature is suitable for methane dissociation, which usually occur at 700 degrees Celsius. And to increase the reforming reaction inside the device, usually researchers apply an additional layer which contain catalyst to increase the methane reforming inside the device. However, in developing the system, a single cell is not enough to power up an application. So usually, we combine the single cells using a critical component called interconnect. The interconnect has two main functions, and the first one is to act as an electrical conductor between the single cells, and the second one is to act as a barrier to separate the fuel and the oxidant, which is flowing at the anode and cathode respectively. So today I will discuss on this particular component, which is the interconnect, and how to develop the interconnect further in order to increase the methane reforming inside the solid oxide fuel cells by applying a catalyst on the surface of the interconnect. So here, in developing the solid oxide fuel cells, recently more noble material which have higher ionic conductivity was discovered, which allow the operating temperature of the solid oxide fuel cell to be reduced below than 800 degrees Celsius. So this major breakthrough allows material displacement for the interconnect from the ceramics to alloy metal. And up to date, the most potential candidate as the interconnect is the ferritic stainless steel. This is due to its benefits over the ceramics in terms of manufacturing cost, commercially available, high chemical resistance and conductor, and also good mechanical strength. However, when this material is exposed to the solid oxide fuel cell environment operation, it has several limitations. So the first one is the growth of oxide scales. This oxide scales is highly rich with chromium, which is highly volatile when exposed to an environment that have high oxygen partial pressure. So this chromium volatilization can cause poisoning, which is the second problem of the material, towards the neighborhood components, especially on the cathode, because at the cathode environment, the oxidant is flowing through the component, which have high oxygen partial pressure compared to the anode side. That's why on the cathode component, this problem is more severe compared to the anode side. To overcome this problem, a protective coating is suggested. From the three material, which is the perovskite reactive element and the spinel is widely preferred because of its effectiveness, especially in preventing chromium migration towards the neighborhood components. However, as mentioned earlier, since the problem is more severe at the cathode side, most of the researchers studied the spinel behavior only at the cathode side. In the recent reports, there is findings shows that the oxide scale growth also can occur at the anode side. Even though the growth is not as rapid in the cathode side, it still can contribute to the poisoning of the anode, which can degrade the cell and also lower the performance of the solid oxide fuel cells. So in our project, we suggest the coating not only at the cathode side, but also at the anode side. However, when we consider the spinel coating at the anode side, which is the reducing environment, we must consider the other one potential of the spinel, which is not only as a protective coating, but also as a catalyst for biogas reforming. This is due in the spinel development, the transition metal frequently used, such as Fe, CO, and manganese, as shown in the picture. For this particular research, we choose nickel, copper, and manganese due to the benefits of each element in contributing for the reaction of metal reforming. For example, nickel, which is the most preferred catalyst for metal reforming, is because it has highly reactive with carbon, which can help for CH4 dissociation. However, this active metal also is the source of carbon deposition, which can cause the catalyst deactivation. So, in order to combat this problem, we partially replace nickel with copper and manganese, which have lower reaction towards carbon and is expected to prevent carbon deposition on the catalyst. When we considering spinel as a catalyst, we must also look into its structure. So normally, spinel is represented with normal structure where the divalent ions resides more in the tetrahedral sites. However, there is evidence shows that each spinel have a certain degree of inversion where the spinel exists in an inverse form where the divalent ions, which is usually made up of the active metal, resides in the octahedral sites. So these benefits allow the active metal to be exsoluted during the reduction process, especially in the anode environment, which is in the reducing environment. So when the exsolution occurs, it allows the outward diffusion of reduced ions, which is from the active metal, onto the surface of the catalyst. This helps in the dispersion of active metals on the catalyst. And by having this structure also, it is expected that it can increase metal support interaction in increasing the chemical stability of the spinel for a long-term operation for methane reforming. Now, in our cases, we discovered that the spinel have many synthesis techniques that is used by the previous studies. However, in our case, we use glycine nitrate process due to its advantages compared to the other techniques in terms of moderate setup, cost-effective, less energy step, and fast production. And the most important one is it can easily produce homogeneous and pure powder. And this synthesis technique also can be easily scaled up for industry purpose. However, when we study this technique, we have to consider the three main parameters which can influence the structure of the spinel. The first one is the mixing time, followed by the glycine nitrate ratio and also the calcination temperature. For this presentation, I will focus more on the mixing time, which is the first part of our project. Therefore, by this presentation, I hope to elucidate the influence of mixing time, not only on the structural properties, but also the reducibility of the nickel copper manganese spinel catalyst, which produced through the GNP process. In terms of phase structure, we can see that all the samples, even though the mixing time is different, produce a cubic crystal system and a highly spinel structure without any secondary structure. However, it have secondary phases in a small amount, which shows that these spinel also have a certain degree of inversion inside its structure. And we can see that through the high speed, there is no significant changes where there is no peak shift. So this means that there is no significant changes in the structure by the mixing time. However, we can see that the main phase is different, where it's increased until 24 hours of mixing time and then start to decrease again. So this can be explained by the difference of distribution of the elements inside the spinel, where 24 hours is determined to have the most effective mixing time in producing a good distribution of the elements. And this is supported by the Edx analysis. As you can see here, at the 1 hour mixing time, we can see that the nickel especially is not distributed well enough that it seems to be agglomerated on certain part of the spinel. As the mixing time increased to 12 hours, we can see that the elements start to distribute well enough, and it is increasing after 24 hours. And after 24 hours, we can see that distribution, there is no significant changes, meaning that at 24 hours, the element started to distribute at the maximum capacity, that no significant changes was observed. So from these two analyses, we can see that a minimum of 24-hour mixing time is required, not only for homogeneous element distribution, but also to have a high main phase presence in the structure of the spinel. Now, so we can see that the difference in the structure also can affect the catalytic activity of the catalyst. So here I show you the hydrogen temperature program reduction, which is an effective analysis to determine the catalytic activity of each spinel, and this reduction behavior is closely related to its methane reforming performance. So the better the reduction behavior of the spinel, it is expected that it will have higher methane reforming performance. So for these figures, the three main things that we have to observe is the intensity of the peak, the location of the peak, and also the peak shift. So here we can see that the high and sharp peak was indicated by the 24 hours mixing time. It shows that this spinel have the highest or the fastest absorbance of reactant, which can help in fast methane reforming. Also, we can see that the peak shift towards the high temperature for 24 hours mixing time, indicating that this particular spinel have high strong metal support interaction, which can help in increasing the stability of the catalyst. And also it have the highest intensity, which also increase that there is a phenomenon called hydrogen spillover, which help in increasing also the catalytic activity of the catalyst. So here the figure shows the final structure that is expected after the reduction process, where the reduced nickel and copper active metal, which is extracted from the spinel, is supported by the manganese oxide matrix as the final product of the nickel copper manganese spinel catalyst when it is exposed to the anode environment in the solid oxide fuel cells. So this is expected to help in increasing and also combating the carbon deposition, and also at the same time have high methane reforming during the solid oxide fuel cells operation. So when compared to the other catalysts produced from previous researchers in various applications, we can see that the present study have have significant lower reduction temperature compared to the nickel-based catalyst produced in the past research. So the main reason is the absence of alumina oxide inside the present study, because this material is known to have a very stable spinel formation that is hard to be reduced, even though at a very high temperature. Meanwhile, when we compare to the catalysts that have lower reduction temperature compared to this catalyst, is because they use reduction promoter metals such as platinum or magnesium, which can help in reduce further the reduction temperature of the catalyst. However, we determined that the present study is already enough for the solid oxide fuel cells, because solid oxide fuel cell operating temperature is at around 600 to 800. So therefore, the reduction temperature already lower than the operating temperature of solid oxide fuel cell, which consider the spinel is already enough to be used for the solid oxide fuel cell application. As a conclusion, the first one, that the inverse nickel copper manganese spinel can be produced via GNP technique, where the spinel can be reduced at a very low temperature compared to the previous studies, and it is expected that this spinel can act as a catalyst for solid oxide fuel cell application. Before I end my presentation, allow me to acknowledge Ministry of Higher Education Malaysia for awarding us a grant to conduct this research, and CREAM UKM for their excellent facilities. Thank you very much.
All right, thank you so much, Mr. Ishraf, for the very interesting presentation and for being on time. Now I would like to open to the floor. If you have any questions, you can ask directly to Mr. Ishraf.
Hi, Ishraf.
Hello, yes.
Can you explain about the spinel? You have inverse and normal.
Yes.
Inverse. Can you explain what is the special characteristic between inverse spinel and normal spinel structure catalyst that you have done?
Thank you, Doctor. That is a very good question. So as explained earlier, we have, for the spinel, there is a normal and inverse spinel. So the normal spinel, usually the divalent cations resides in the tetrahedral sites. So when this cation resides in the tetrahedral sites, it is much more harder for the spinel to be reduced. This is what happened for the alumina oxide earlier that I explained. Why the material is hard to be reduced? Because most of the divalent ions is reside in the tetrahedral sites. So when the active metal cations reside the octahedral sites, which is much closer to the surface of the spinel, it is more easier to be reduced, and for the outward diffusion of the ions. So a much lower temperature is needed to reduce the spinel in order to allow the extrusion process. So whatever when we want to consider spinel as a catalyst, we have to consider the feasibility of the spinel to be reduced at a much lower temperature. So in this case, we choose a spinel which have a high degree of inverse spinel, because we want more acceleration process happen during the reduction treatment. Thank you.
Okay.
Hope that answers the question. Yeah.
Can we ask one more? Isha,
Sure.
other than structural properties that you have studied in this work, there has any another properties that you carry on in order to sustain the spinel, in order to sustain the stability of the catalyst?
Okay.
Another properties.
That if in order to maintain the spinel structure, so we try to manipulate the structure to have a higher degree of inversion. So as mentioned earlier, we use GMP technique, and there is 3 parameters that can influence the structure, which is the first one is the mixing time, the second one is the GMP ratio, and the third one is the calcination temperature. So in this case, for our continuous study, we will proceed with the GMP ratio in order to see how this parameter influence the inversion degree of the spinel. And the third one is the calcination temperature. So the third one is already studied by the previous research for the other spinal elements, and we can see that the third parameter, which is the calcination temperature, is the most effective way to control the structure, because the higher the temperature, the higher the spinal formation. However, we still do not determine yet whether the spinal is in normal or inverse form. That's why in our project, we also consider to study the calcination temperature in order to see the inversion degree of the spinal. Hope that's answered the question. Thank you.
Okay. Thank you, Isha.
You're most welcome, Doctor. Thank you.
Any more questions from the floor? Okay, I guess that's all, Ms. Isha. Well done. Okay, let's move on to our next presenter, Dr. Susmita Pramanik, with the paper entitled Flexible Polymeric Electrode Embedded with Nanostructured Sensing Material for Simultaneous Detection of Adenine, Guanine, Thymine, Cytosine for Medical Diagnosis. The floor is yours.
Madam Susmita, you may share your slide and also
Hello.
hello, we hear you.
Yeah. Good morning. Good morning, everybody. Sorry about that little bit of internet connection glitch. So I am glad to be accepted as for my paper presentation in this international conference. Give me one moment. I'll just quickly share. Is the screen visible?
It's visible.
All right, so today I'll be presenting our current research work, which is in collaboration with the University of Malaysia, and it is based on flexible polymeric electrode embedded with nanostructure sensing material for simultaneous detection of adenine, guanine, thymine, cytosine for medical diagnosis. So mainly this research, this is the contents of the presentation. It is based on nanoparticle modified electrochemical sensors, and these sensors have become very desirable because they have diverse type of properties, as they are able to detect trace quantities of materials, and while simultaneously they are very selective. So they have a high surface area, good conductivity, and efficient electrocatalytic activity. And this is the reason sensors have become very integral part of today's technology in medical field and biomedical field and chemical field. So these sensors, they are able to detect molecules of organic or inorganic nature, and they can detect at very trace quantities, and as well as they can detect any kind of biological molecule in biological fluids, man-made mixture in pure or complex forms, and they can also detect disease marker molecules, which is a difficult task using orthodox methods. And a very fast processing of purification of the molecules can be purification and detection can be done using these sensors. And the most added advantage is that the detection is very specific and selective. So generally sensors are divided into two main classes. In our study, we initially in our team we used to work on solid sensors, but in this project we moved on to flexible polymeric sensors. The solid sensors that we would create used to be using the nanoparticles that we synthesized, and we would mix it with graphite in a mortar and pestle, and we would mix it in the ratio of 1:4, and then using a paraffin as a binder, make it into a paste, insert into glass capillary tubes to make these solid electrodes. But the solid electrode drawbacks, which led for us to move to polymeric sensors, are that they have a small surface area of mostly 1 millimeter diameter at the tip, and this is not easily modifiable. And the reactive surface being so small, with easily gets reacted or used up, and cannot be reactivated easily, and because it has a rigid structure, its modification is also very hard. Another big drawback is that because they are solid in nature, and cannot be used for multiple times, they are not very cost effective, and a large scale production is not feasible. So here comes the need for flexible sensors. When the most desired advantages of a flexible sensor are that they can be synthesized in any shape, size, form, and they are structurally very flexible and cost effective. Mass production is can be done very easily, and they can be altered according to whatever surface area is required. The response to stimuli is very good, and they can be embedded using any circuitry, and they can have different types of displays or forms, so that makes it very desirable in the biomedical field. So in our project, the nanomaterial of choice that we used were mixed oxides. In mixed oxides, what we used were orthoferrites of rare earth metals and spinels. The reason for choosing these were that they are very electrochemically stable for different processes, and this is because they have a high band gap, and but one issue is that they are not very conductive. So in order to make them conductive, graphene is used as a filler, because it has high background conductivity, and it can be easily used as a modifier in any paste preparation, and it disperses well in any kind of polymeric matrix. Our project, we chose selectively gadolinium ferrate, lanthanum ferrate, samarium ferrate, and nickel magnet molecules. These are the crystal structures of these molecules, and so we for the synthesis of these nanoparticles, what we used is called the combustion synthesis method. Generally, nickel nanoparticle molecule synthesis is either bottom up or bottom down. We use the bottom up approach as it creates nanoparticles which have a good narrow size distribution and small particle size ranging from 20 to 50 nanometer, and they are easily dispersible in polar organic solvents such as dissolve in silicon polymer easily. This is the process that we use to create the nanoparticles. Basically, we heat vigorously a mixture of the oxide of the metal oxides in the presence of sugar, nitric acid, and monoethanolamine. The reason for using nitric acid and monoethanolamine is because they create a very explosive kind of reaction mixture, and which allows to vigorously get the reaction going, leading to a black fluffy mask at the end, which is then calcined in a muffle furnace, and the end product is gives us the nanoparticles. So we did characterization studies of these nanoparticles using XRD, FESEM, and TEM. And XRD results showed us that the crystal structure was a pure phase crystalline structure of the nickel manganate, and FESM and TEM results showed us the size of the nanoparticles and its morphology and its size distribution. So for our project, to make these polymer-based flexible electrode, we chose polydimethyl siloxane, also known as PDMS, as our choice of polymer. This is also known as dimethyl polysiloxane or dimethicone, and it's a polymeric organosilicon compound, also commonly referred to as silicone. It is widely used in silicon-based organic polymers due to its versatility of properties. It can be manufactured at various viscosities, and this is due to the siloxane linkages that is present in the compound formation. Easy fabrication of the flexible polymer with the embedded nanomaterials in it can be done using this polymer. Added advantages is that it has low interfacial free energy. It is chemically inert. It has good thermal stability and gas permeability, optical transparency, and easy to modify its surface properties. So for the synthesis of this electrode, this polymeric electrode, what we did is we mixed it in chloroform, as it's highly miscible in chloroform. We used graphene also mixed in chloroform and vigorously mixed it and cured it in a glass plate, and it was then vacuum vaporized and heat curing was done at around 150 to 200 degrees Celsius to form the polymer. Then the characterization of this polymer was done using SEM to see the distribution of the nanoparticles and graphene inside its matrix, and it was seen that it was beautifully uniformly spread throughout it. So this is how the polymer is made. On the left hand side you can see the plain polymer, plain PDMS polymer which we did on a glass matrix, and on the right hand side is the nanomaterial and graphene embedded one. And these sheets can be made of various sizes. Once we have synthesized these and heat cured it, we cut strips out of it, and then we connect it to a platinum wire, and as per the circuit needs we would make them into a small electrode sort of a probe. So the biomolecules of interest that we use to detect is adenine, guanine, thymine, and cytosine, because they are very important nucleic acids and building blocks. They are essential in disease detection, and they also lead to disease detection even before the onset of its symptoms. So it becomes very essential for the detection of these molecules. Now, the part one of our project, we use nickel manganate nanoparticle graphene embedded PDMS electrode for the detection of guanine. We after that we did electrochemical analysis. Cyclic voltammetry and differential pulse voltammetry was the standard method used in the presence of zero point 0.1 millimolar guanine and in phosphate buffer saline of pH 5 at 0.1 molar. The scan rate that we found was for the cyclic voltammetry 100 millivolts per second, and for differential pulse voltammetry we got 50 millivolts per second. Then we did pH variation studies for pH 4 to 6. Beyond 6, due to the hydroxyl ion interference, didn't give good peaks, but up to 4 to 6, it gave very good results. And we also did a scan rate variation from 5 to 500 millivolts per second for guanine. At 0.1 millimolar concentration, and it also gave a good rise in current as we varied the scan rate. So in conclusion, in the first part of the project, we found that after 40 days, when we performed repeatability tests, there was consistency in the data, and also reproducibility test was done using the freshly prepared electrode again, and that also showed very consistent results. So we realized that degradation of the electrode is not taking place, and the detection range that was found was around 300 nanomolar. So using conventional solid electrodes gave around that much value. So in conclusion, we understood that these polymer electrode is also giving good value. In the next step of this project, we will need to then analyze the adenine, thymine, and cytosine molecules using the other orthoferrites, which is the gadolinium ferrate, lanthanum ferrate, and samarium ferrate. We were also yet to do the mechanical property studies and characterizations. So at this stage, I would like to acknowledge Department of Chemistry, GLA University, and University of Malaya, as we are doing this research in collaboration. And our laboratory facility and all materials and equipment is being provided by Department of Jadavpur University, Department of Chemistry in Kolkata. And thank you. I would like to end the presentation here.
Thank you, Dr. Susmita.
Thank
Can
you.
we questions from the floor, please?
Hi, Susmita.
Hello.
Susmita, you examine about flexible polymeric electrode, right?
Yes.
Or this flexible polymeric is used for purposely for detection disease. This is right.
Yeah, that's right.
Detection disease when you detect biofluid molecules
Yeah.
such as guanine, cytosine, thymine, and etc.
Mhm.
May I know what the specific disease can be detected after detection these biofluid molecules? Specific the detection
So
of disease.
yeah. So basically, what these polymeric electrodes, actually these polymers are used in many types of sensors, and what we are doing is we are detecting the nucleic acids. Now, nucleic acid concentration, like low concentration, it can show actually the prognosis of many diseases. So that is what we are doing, because ultimately nucleic acids concentration varies, shows the variation of different biomolecules. And when we can detect the changes in the nucleic acid, then those results can be interpreted later on when the sensors are developed. They can then allow them to see which molecule concentration is varying, and then depending on that, then they can assess what kind of disease markers they can look up. So at the moment, we are only focusing on the basic nucleic acids, not disease molecules or markers.
Okay, thank you. Terima kasih.
Okay, we have another question from Dr. Hanani. Thank you, Dr. Sushmita, for the presentation. I have a question which is, I have discovered that guanine, adenine, thymine, and cytosine have also been electrochemical detected by graphene oxide nanoribbons. May I know whether it is comparable with your study? Maybe you can give some comments on that. Thank you.
Sorry, can you repeat the last part?
May I know whether it is comparable with your study?
What is comparable with our study?
Okay, guanine, adenine, thymine, and cytosine have
Yeah.
also been electrochemical detected by graphene oxide nanoribbons. Is it
Okay.
comparable to your studies?
Yeah, it is, because the polymer that we have synthesized, we can make those into ribbons or strips or chips, anything, and then we can connect it electronically, make it into a circuit. So it is comparable. But in our project, we have only completed one molecule, which is guanine. So that is the step one of the project, and then we will move on to the detection of the other molecules. But yeah, it is comparable.
I have one very small question. Do you think this can be applied other than medical field, maybe in food detection?
Yes, so sensors, generally electrochemical sensors are used in any kind of molecular detection in soil, in industrial effluents, in even in chemical composites, or even in industrial mixes. They have a huge plethora of uses in diverse fields. Even in agriculture, soil biology, environmental chemistry, they can be used.
All right. Thank you so much, Dr. Sushmita, for your presentation and all the answers. Okay, can we move on? All right, we move on to our next presenter, Dr. Huda M. Al-Nawawi, with her presentation entitled A Systematic Review and Meta-Analysis on the Properties of Nano-Calcium Silicate-Based Cements.
Okay. Good morning. Assalamualaikum and good morning for all. My name is Dr. Huda Nawawi. I'm PhD student in dentistry, faculty of dentistry, UM. Let me share my screen. Okay. You can see my screen now?
Yes, we can see your screen.
Okay. Our topic today is a systematic review and meta-analysis on the properties of nano-calcium silicate-based cements. Okay. The introduction. I know we are not all dentists today, so briefly, our tooth structure is in a difficult medium, which is always in water, in fluctuating temperature and fluctuating pH, in continuous need for calcium, and under several forces. So any material we have to choose for filling this two structure has to fulfill all these properties. It has to be biocompatible, good sealing ability, endurance, tissue formation, acceptable bond strength properties, microbial activity, and doesn't interfere with most restorative materials. So now today we will talk about mineral trioxide aggregate, or MTA. MTA is a kind of calcium silicate cements. Calcium silicate cements were first introduced in dentistry by Torbenjad in 1993. It had two forms, a gray and white MTA, which was introduced for better aesthetics. So the composition of MTA is briefly 20% of bismuth oxide and 80% of refined Portland cement. Namely, it is tricalcium silicate, tricalcium aluminate, tricalcium oxide, silicate oxide, and bismuth oxide. These are the clinical applications of ProRoot MTA. We can use it over the pulp as pulp capping, fortification perforation, root repairs, and epixification. So MTA is a good material, but it has many drawbacks, like long setting time, which can be up to 40 minutes to 2 hours, which is too long for our dental visits. It is quite expensive, as you can see. It's more expensive than gold. It causes tooth discoloration, even the white MTA, like can be seen here. It is soluble in acidic medium, causing these porosities, and it has poor handling properties, just like sand. So by introduction of nanotechnology, we can detect that if we make this material in the nano range of 1 to 100 nanometer, it can increase its effectiveness. Nano-Sized Mta has been invented and patented in USA by Seguiri 2012. It is composed of dicalcium and tricalcium silicate, bismuth oxide, gypsum, zeolite, and strontium carbonate. It is claimed to have better biological, mechanical, and physical properties than the ordinary MTA. So this review provides systematic evaluation of the published studies that examine the effect of nanomodification on the properties of calcium silicate cements. Methodology. This review was undertaken according to the guidelines provided by the preferred reporting items of systematic reviews on meta-analysis, PRISMA. The research question, according to the PICO guidelines, was, do nanocalcium silicate-based cements show better physical, chemical, biological, and antimicrobial properties compared to conventional calcium silicate-based cements? We have selected two databases, PubMed and Scopus, and with 8 keywords, nano-MTA, nano-mineral trioxide aggregate, nano-Portland, and nanocalcium silicate cements, with a space and without a space. Exclusion criteria were, when the articles were out of scope, reviews and case reports didn't include nanocalcium silicate cements of particle size 100 nanometer, or calcium silicate of normal particle size with added nano additives, or not in English language. Meta-analysis. Statistical analysis was performed using reviewer manager software. For continuous data, mean difference was 95% confidence interval. The authors have assessed statistical heterogeneity in each meta-analysis using chi-squared tests. Data was extracted from figures using WebPlot digitizer software. Results and discussion. After removing duplicates, we had 1,174 studies. Then we have excluded 1,153 studies to find out only 21 studies were eligible for being studied, excluding 6 for reasons. So we have 15 studies to see. The 6 excluded studies were 3, the nano cement particle size was unclear. Even after contacting the authors, it remained unclear. And the other 3, the actual particle size was not in nano range. Properties of nanocalcium silicate cements was categorized into 3, physiochemical, mechanical, and biological, which will be discussed in details. Physiochemical properties. Setting time. Nano-MTA has a setting time of 6 minutes compared to 43 minutes of white MTA. Nano-Mta was significantly having lower solubility than white Mta even at low pH of 4.4. This was attributed to the increased surface area and finer particle size. Nano-Mta showed higher pH values compared to white Mta, especially in the first 24 hours, which are the most important in dentistry. In addition, calcium ion release increased significantly for Nano-Mta compared to white Mta. This was attributed to the increased formation of calcium hydroxide, which can liberate more calcium ions from Nano-Mta and raise the pH value. Mechanical properties. 8 studies have examined mechanical properties of Nano-Mta, as well as 1 study examined the mechanical properties of tricalcium silicate cement. Of these properties were microhardness, vigor, indentation, compressive strength, shear bond strength, and push-out bond strength, which has 4 studies and was selected for the meta-analysis. From the meta-analysis, despite the heterogeneity of the results of the 4 studies, all of them favored nanocalcium silicate cements rather than calcium silicate cements. Nano-Mta was found to have higher compressive strength and microhardness under different conditions, such as low pH and thermocycling compared to white Mta. To explain this, the nano-sized particle size increased the surface area of the cement, caused rapid hydration, shorter setting time, and so better interlocking in the mass of the cement structure and a less porous cement, so enhancing the physical and mechanical properties. It also caused more uniform distribution of particles and improved orientation of the intringite crystals. In addition, zeolite, which is added to Nano-Mta, is a crystalline hydrated aluminosilicate of alkaline metals and metals of alkaline soils, which acts as a stabilizer, having a buffering effect, allowing the material to exhibit smaller and minor porosities. Bismuth oxide is added to Mta or Nano-Mta for radio opacity. In its biggest size, it has a deleterious effect. But in nano size, it showed that it has no deleterious effect due to the decrease of particle size, which makes it distributed regularly, resulting in a more dense structure and solid and less unreacted water. Biological properties. 5 articles reported the biological properties of nanocalcium silicate cements. It showed that there was significant decrease in inflammatory and foreign body reactions. It improved bone healing ability, bone mass density, and increased angiogenic activity. This might be due to the setting reaction of Nano-Mta, which causes release of calcium and hydroxyl ions during hydration and causing rise in pH. In addition, the alkaline properties of Mta and zeolite lead to neutralization of the acidic metabolites of macrophages and osteoclasts. Important things to highlight: misnomer and lack of details. All the present studies, except one, use the term Nano-Mta, although their cements don't represent a reduction in the particle size of the original Mta developed by Torabenjad in 1993 or the commercial Pro-Root Mta. In all his studies, Segheri et al. Used the term Nano-Mta for his nano-sized cement, which is composed of dicalcium, tricalcium silicate, bismuth oxide, gypsum, and zeolite, and strontium carbonate, which is chemically different from the Mta. Another thing, in Abdelhamid et al., they compared 2 nano-tricalcium silicate cements manufactured through salt gel and solid-state reactions, and this study lacked comparison with the original size Mta. For verification of nano-sized particles, 2 studies used TEM, which are Abdelhamid et al. And Nagy et al. Abdelhamid et al. Found that salt gel method had less particle size than solid-state reaction. 1 study used particle size analyzer in addition to SEM, which is Effendi et al. In his SEM, we believe this is too hazy to see the particle size through it. Segheri et al. Actually had 12 articles out of the 15 we had selected in this review. And he referred in all his studies to his patent 2012 and 2014. He claimed that particle size is 40 to 100 nanometer. and he claimed this through this particular SEM. Finally, for all studies, major experimental details during fabrication, such as number of replicates done, material stabilization, and proper verification of size, is not described. Conclusion: currently, the evidence available for properties of calcium silicate cements in nano range is limited. Despite the favorable properties found through this review for nanocalcium silicate cements, it could be a result of additives, not of the actual nano size. Recommendations: characterization of nanomaterials can be challenging. All the aspects of characterization process should be carefully documented to ensure transparency and reliability of the results. According to ISO TR 10993-22, for materials to be categorized nano, it should be 1 to 100 nanometer and no more. Nanomaterials are usually highly reactive and subject to agglomeration and aggregation within a short period of time. For this reason, single characterization method might not be enough. Complementary method like SEM, TEM should be implemented in the studies. The availability of positive and negative controls for samples are a must for reproducibility and reliability of testing. Thank you.
Dr. Huda. Okay, I
Thank
would
you.
like to invite for questions.
Hi, Dr. Huda.
Hi, Doctor.
May I know, can we, okay, sir. You use the software like web plot digitizer
Yeah.
to review your, to make review for your study.
Yes.
Can we use this software also for another case of study?
Because my study results were not homogeneous, so this one was the most suitable for this study.
Okay. What is meta-analysis? Can you explain more about the meta-analysis that you have done?
Okay. When we have a number of studies that have a common property, and we want to compare the results of this property, like I have chosen the shear bond strength. But actually, the authors in the 4 studies didn't use the same range of the strength. So we want to compare these studies to see the average bond strength, actually, the average shear bond strength, so we can end up with the result. Is it significantly higher or not?
Means for a meta-analysis by using the digitizer software. That's right?
Yes.
Okay. Thank you.
Thank you.
Any more questions? Okay, Dr. Huda, I cannot help but I want to ask this question. Okay,
Yeah.
compared to the normal MTA, do you think the nano MTA would be cheaper?
Nano MTA, we don't know yet because it's still not a product. But actually, my PhD is working on a material similar to it, and its main aim to make it cheaper and to be a Malaysian product, so everybody can use it, because MTA is has many drawbacks, and it's also more expensive than gold.
All right, thank you so much, Dr. Huda. I think that's all questions for you.
Thank you.
Okay, thank you so much. Okay,
Thank you.
now thank you to all the presenters for the session. We have our last presenter, we are very lucky to have him as our invited speaker today. I would like to invite Dr. Muhammad Shahadan bin Muhammad Suwan with his paper entitled Synthesis and Characterization of Black Phosphorus via Ball Milling Technique, Effects of the Milling Materials. Dr. Shahadan?
Okay. Thank you, Dr. Nina.
All right.
Okay. Okay, I hope you all can hear me clearly ya.
Yes, we can hear you very clearly.
Yes.
Maria okay ya? Dengar. Long time no see
Yeah.
our colleague in here.
Yeah.
Like Dr. Nani, Dr. Maria, and all becomes doctor already.
Alhamdulillah.
Oh, okay.
Alhamdulillah.
For my slot today, I just want to share my my point of view about the about a new type of what we call in here type of nanoparticles or type of nano things, what we call it phosphorin. But before we learn further ado about the phosphorin, we need to know what is the mother of phosphorin, which is some kind like for graphene, we know it comes from graphite, right? But for phosphorin, it's coming from black phosphorus. I hope you can see this slide. Anyone? Okay,
This slide,
clear.
Doctor. Yeah, very clear.
Okay, thank you. Okay, this is my title today. Synthesis and characterizations of black phosphorus via ball milling technique, effects of the milling materials. So my name is Muhammad Syahdan Muhammad Swan. I'm from the Faculty of Manufacturing Engineering, Universiti Teknikal Malaysia Melaka. Jiran lah Dr. Hanani punya jiran. Yeah.
Yes, correct.
Okay. It's a little information about me. I'm the alumni of UM under Prof. Rafi Johan. So I think there are so many alumni from graduate from under the same roof with me. So we will pursue or we will continue to what we call to find what is the best thing about the nanoparticles in here or nanomaterial. So this is my contents. First of all, I would like to introduce a little bit about the background of black phosphorus, properties and behavior of black phosphorus, synthesis method, results, and conclusions. But before I begin, I would like to I apologize because my presentation today is not completely what we call it's not complete because in fact of the COVID situation in Malaysia and also in Melaka, so I cannot proceed with other characterization. So I will share with you what I have done in the past year. So what is black phosphorus? Everybody know about the graphite, right? Graphite, graphene. Even Dr. Sushmita talked about graphene. She added in the polymer, and also many of us like to use graphene because that one is the new type of, or the potential nanoparticles, but we cannot just focus on one nanoparticles or nanomaterial. We need to move on. So I try to move a little bit. So I found that the phosphorin find to be interesting what we call nanomaterial. But before we go deep into phosphorin, we need to know the original what we call material of phosphorin. The phosphorin coming from the black phosphorus, the black phosphorus. So what is black phosphorus? A bulk layer of phosphorin. Phosphorin is one layer, but black phosphorus is layers of phosphorin. Just like graphene, graphene is a layer of graphite. So graphite is layers of graphene. It's coming from the phosphate rocks, phosphorus, and we synthesize into the black phosphorus. So this is the little bit about the history of phosphorus. It's discovered by, I don't know who discovered this, in 1669. So And then it extract phosphorus from phosphate rocks, successful synthesis of black phosphorus, and finally in 2014 introduction of phosphorine. They successfully exfoliate the black phosphorus into phosphorine. So we want to know the potential of the phosphorine, the bulk material all around the world. We can see in here the percentage and of phosphate rocks reserve distribution in the world. So have about half of the phosphate rocks is coming from Morocco or in the Western Sahara. But I think Malaysia, no phosphate rock in Malaysia. So no worries, we can buy it from the other countries. There are 68 billion tons of reservoir of phosphate rocks. So we need to use of this reservoir to make it function. So after we get the phosphate rocks, we can synthesize into 3 electrodes of phosphorus. The first one is white phosphorus, red, black. So which one is dangerous? Of course, the white phosphorus, because the white phosphorus we are using it to make a bomb, such as what we call the Israel. Israel use the white phosphorus bomb to bomb the Palestine by using the white phosphorus. It became very dangerous because it will spontaneously burst into flame when react with the air or the atmosphere. So this one is very dangerous, white phosphorus. Then the red phosphorus. The red phosphorus is non-reactive with air. It's commonly used to make matches and also the burning material. And what we want to have is the black phosphorus. It's black crystalline solid, non-reactive with air at 25 degrees C, and melting point is quite high. It's similar to aluminum. It's about 610 degrees C. Okay, black phosphorus is the most stable electrode of the phosphorus element at ordinary temperatures and pressures. So the Bridgman successfully obtained black P for the first time in 1914. So by using the pressure of 1.2 gigapascal, is very high pressure, and at elevated temperature around 200 degrees C. Then by discover this kind of allotropes or black phosphorus, the Bridgman awarded as the Nobel Prize in 1946. There are only about 100 publications in the past 100 years of black P to our knowledge. So after, although the black P is discovered a long time ago, but there are only a few publication about it. Okay, this is much interesting data. We buy the phosphate rocks about USD 77 USD per metric ton. So after we synthesize to black P and get the phosphorine, we can sell it 750 per 100 gram. So I think this one is much expensive than the gold because of its potential application, and also how difficult it to synthesize. So for those who are invested in gold, maybe you can try to invest in phosphorine. Okay, betul tak, Maria? Okay, properties of phosphorine. I go quick on this. Structural properties. The phosphorine compared to the graphene is flat surface. Graphene has a flat surface, but phosphorine they have a bucket layer. They have an armchair in here, so they quite difficult to agglomerate or to aggregate, such as like Dr. Huda said just now, the nanomaterial tend to aggregate or agglomerate because it has a high surface area or high surface energy. So it tend to agglomerate and aggregate. But for phosphorine, it has a bucket layer in here. Even though the layers stack to each other, but they tend to what we call uniformly distribute because of this kind of structure. Difficult to segregate or agglomerate. So they have an isotropic properties in here, and also they have electronic properties. Compared to the graphene, the phosphorine have a electronic properties. For example, they have the mobility in here, and this is the comparison between the uh, graphene, black phosphorus, and also the charcoal metal dichalcogenide. Sorry, we have in here three types of 2D materials. They are for researchers nowadays. They're very interested in using graphene, but they have potential in black P. Okay, and what is more interesting data is the black P have the band gap in here compared to the graphene and the MDC. For graphene have zero band gap, but for black phosphorus it's around 0.3 to 2.0 electrovolt. For TMDC is 1.5 to 2.5. So it's very have potential for many applications. And for mechanical properties, since the black P or phosphorine have the structural or armchair or bucket layer structure, they have different mechanical properties at different direction. So they have higher properties, mechanical properties in zigzag direction. Okay, and phosphorine or black phosphorus, I call it BP. BP is can be used to solve the limitation of graphene. So graphene have zero band gap, flat sheet structure, and low on-off ratio. All these limitation can be solved or prevent by using the phosphorine. Okay, this is some kind of future applications, not yet applied in real application, but it can be in our future application to be as thermoelectric, which is convert the thermal or heat into electricity to be used in the sensor, photosensitivity, transistor, and also energy storage. Okay, synthesis method. This is the difficult one. Since bulk BP is classified as van der Waals material, similar top-down technique as those employed to produce graphene using graphite as the precursor can be also applied to make phosphorine from BP. So we have two ways in producing the BP. The first one is by using the white phosphorus, which is the easiest one. By using the white phosphorus, we can have the black P by using high pressure synthesis, high speed ball milling, and short transport reactions. But as I said just now, white phosphorus is very dangerous. So we go to the other way, is red phosphorus into the black phosphorus. So to obtain the BP from RP, we need to have a high pressure in and be press, and also sonication, which further lowers the cost and amplifies the production process. Okay, this is the example of producing the BP from the RP by using this kind of setup. Liquid exploration and pulse laser deposition technique, which is pulse laser deposition technique is very expensive. The setup is very expensive, while the liquid exploration is very complex method. So this is the phase problems by this kind of nanomaterials. First one, it's high complexity of what we call synthesis method is very high complexity. Black phosphorus was synthesized from amorphous red phosphorus using copper as a catalyst. They add something like this, lump, and they're very complex in here. And finally, we transfer into a silica glass. The one is very complex. We don't talk about the parameters yet. We need to control the atmosphere, the temperature, the humidity is very complex. So we are using the white phosphorus, although it's easy, but as we know, the white phosphorus is very high risk because it easily react with the air. So we cancel the white phosphorus. We try to use the red phosphorus. And then by using the expensive method such as pulse laser deposition, something like this, very expensive. If you have this kind of a setup, you can go for it. Kalau tak ada, if you don't have something like this in your lab, so it's it's very difficult to produce the BP. And one more exciting fact is black phosphorus is expensive compared to their to the RP. Black P is about 4.8 million RM per per gram, sorry, per kilogram in here compared to the red phosphorus. So in order to have the BP with simple, no toxicity, not expensive, no complex processing method, and by using the RP, we have produced the BP by using high energy planetary ball milling. We call it ball milling process. But at long period of high speed milling process, the jar or the medium that contain the RP must be studied. So in my research, in the study, we will study the effect of by using different kind of jar or different kind of jar materials. So we will synthesize the black P by using RP with mechanical ball milling. The duration of milling time will be 2 hours, and milling speed is around 500 RPM, which is a very high speed of ball milling. Ratio of grinding ball to red P is 500 gram to 1 gram. Okay, this is quite small because if we want to produce 1 gram of BP, we need to use very many balls or this kind of weight of the balls, 500 gram. The quantity of stainless steel grinding ball is 20, which using this kind of diameter, and we will study the 3 effect of jar. The first one is stainless steel, granite, and the third one is alumina. And finally, we will study the SRD, the Raman, and also the SEM of the synthesized powder. So we have in here the RP. We buy it from the Sima Adrish. We will insert the RP, red phosphorus, into 3 different kind of jar. The alumina jar, granite or agate jar, and stainless steel jar. But in doing so, we will transfer the RP into the jar in the glove by using the glove box, because we don't want the RP react with the air. So once we insert the RP in the jar and we seal the jar and we insert it in high energy ball milling machine. So for the result in discussion, as we saw in here, the first figure in up. In here is the raw red P. The second one is the granite medium. We can see a black and dark brown powder. By using the stainless steel, we can have the very black powder, and also the same goes to the black powder synthesized by using the alumina jar. And for the SRD, we can see in here the alumina and stainless steel have the X-ray diffraction for the BP, as can be seen under this graph. This is the BP line for standard BP line. Black phosphorus line is we know that by using alumina and stainless steel, all the peaks we call signify the BP existence. However, the granite also have the significant peak in here, but they are missing some of the BP peaks. And also the Raman, the expected BP vibrational mode is 340, 40, 430, and 460 respectively, are clearly resolved for samples milling using alumina and stainless steel medium. So the slightly raised background between 300 in here for granite slightly attribute to residual RP for sample synthesized in granite medium. Okay, this is the SAM image. Suppose for this kind of powder, I will go for TEM image, but as I said before, there are the certain limitation because we cannot go rentas negeri. So I just go for SAM image in my faculty. I can say that it not much information I can get from this kind of image, but we can say that the structure of BP obtained in here is flaky. And the discussion, we can say that physical observation, the red into black powder, which indicate the appearance of BP. All the jar can we can have the BP from the RP, but from the SRD, we can say that the alumina has the highest, or the alumina and stainless steel is successfully yield the BP or pure BP compared to the granite, where the alumina has the highest hardness compared to the other medium. It has created high impact energy during each collisions with the balls, and while high temperature formed during collisions and friction was highly sustained because the alumina have a low thermal conductivity, thus optimize the BP transformation. And stainless steel could provide enough condition for RP to transform into BP. Though there is no evidence of impurities in the sample as shown in SRD, but the wear of stainless steel jar is inevitable, actually for a very long period of milling process. If I think if we can further exceed 2 hours, or we go for 3 or 4 hours, maybe there will be some evidence of impurities because of the wear of the stainless steel jar. And the flaky structure of BP is as expected due to compaction between balls and jar. So conclusions for my work in here, I found that the alumina and stainless steel have been used to successfully transform the RP into BP, and the optimal condition of this transformation is achieved by using alumina medium. Okay, that's all. Thank you.
Thank you so much, Dr. Shahadan,
Yeah.
for your presentation. It's absolutely a new information for me, new knowledge for me, especially on black phosphorus and all the phosphorus kinds.
Yeah. If you don't want to invest in gold, you can invest in phosphorin.
Maybe. Okay,
Shahadan,
Yeah.
okay.
why don't you just straight away buying black pea? Don't trouble yourself to change the red phosphorus to
I agree with Dr.
the
Maria.
Okay, Dr.
just straight
Maria.
away buying.
just straight away buying the black pea. Okay,
Yeah.
if I rich like you, I can buy it anytime. As I said before, the black pea itself is already 775 per gram. So if you want
700.
to add it into many application, at least you must buy 100 or 1 kilogram. Correct. 1 kilogram is like
Hmm.
1,000 multiplied by 775 USD. It's about you calculate it yourself lah.
Meaning ni, he's giving us apa tu? Pancing instead of fish lah. Yeah, he's giving us how to come up with BP instead of
Yeah,
just
yeah.
bagi je.
Actually,
yang
actually, I try to buy BP, but the price is very expensive, and we only get a small portion of it. We cannot use that kind of small portion in many application. We want to use it in our, because my future application is want to develop a what we call a cathode material by using the combination of graphene and also the phosphorine, because we know that the graphene is flat surface, it tend to agglomerate and aggregate. By using combination of phosphorine and graphene, we can distribute the graphene well in the cathode material.
okay, I think that has answered also Dr. Hanani's question here. May I know how do you see the future of this black phosphorus? So maybe you have just answered that, yeah?
Okay, Dr. Nani, actually, if you can, if you can synthesize successfully synthesize the pure and also uh, exfoliate the black pea into the phosphorine, you can have many kind of future application. But the concern in here, are we successfully enough to produce the pure BP, and also we ready to exfoliate the BP into phosphorine, because we know that if we want to exfoliate graphene from the graphite, it's quite difficult, right? You need to have a long period of solidification or to have the graphene from the graphite. It's same like the to have phosphorine from the uh, black pea or BP.
Okay, kita nak ikan sikit all the comments from Dr. Noalia, great sharing Dr. Syadan, from Miss Atina Husna. Thank you Dr. Syadan, good sharing. Alright, so we have, okay, Dr. Nani just replied. Yeah, thank you for the explanation. Nice, alright.
Okay.
So we have come nearly to the end of our session today. But before that, of course, I am very honored to announce the best presenter for this session. Okay, are you ready? Okay, the best presenter for session Nanofabrication and Characterization goes to Dr. Susmita Pramani. All right, congratulations, Dr. Susmita.
Appreciate it and thank you very much.
All right, okay.
It was a pleasure being part
Okay.
of this conference, and thank you for at least virtually meeting the part of the University of Malaysia team, as due to COVID we have not been able to go there physically, even though we are collaborating with multiple departments there.
Okay, thank you so much. Sorry, Dr. Syadan, there's another question. Can you just answer that from Dr. Huda? May I know how did you stabilize the particle size of nano RP without agglomeration? Do you think using particle size analyzer is a must or TEM is enough?
Okay, actually, if we want to confirm that our nanomaterial is nano enough, because I know that Dr. Huda tried to produce the nanomaterial, right? The best way is by using TEM to measure the particle size. We cannot use the particle size analyzer, because particle size analyzer is, I think, you just go into the 500 nanometer or 0.5 micron. it didn't go up into the nano size. How did you stabilize the particle size of nano RP? Okay, actually, after we get the black P, or after we get the black P, we will do all the preparation or to insert into application under or in the glove box under control atmosphere. So it's quite we call difficult lah to apply the resultant BP under normal atmosphere. We need to use the glove box because although it didn't react spontaneously with the air, but in the long exposure, it still will react with the ambient temperature, ambient atmosphere. So we need the glove box.
All right, thank you so much, Dr. Shahdan. Okay, now we have reached at the end of the session. Okay, thank you again to all our participants. Thank you to our evaluators. Thank you to everybody who come to
Thank
see
you.
this room, who come to be with us in this room. Okay, on behalf of the MICNC 2021 Organizing Committee, I would like to seek for your kind cooperation to fill out the feedback form as given by session moderator in the chat box. You are invited to join the technical talk later, and I hope to see you again, inshallah. All right, thank you so much. Assalamualaikum warahmatullahi wabarakatuh and good afternoon.
Salam.
Thank you very much.
Salam. Thank you semua.
Tak ada cendol ke?
Thank you, everybody.
Oh boy.
Thank you all. Balik makan rumah lah.
Virtual cendol.
Cendol KFC lah belakang.
Bye-bye.
Bye-bye. Thank you.